astrophysics. I actually got my PhD in particle physics in 1993. Don't tell anybody that. Were you guys alive in 1993? And I did a postdoc in particle physics at the accelerator in Illinois, which is called Fermilab. And then I was, looking for a job, and the job that came up was like not exactly what I wanted. It was another postdoc in the observational cosmology group at Berkeley. And so I spent 5 or 6 years up there working with 2 guys who've now won the Nobel Prize for their work on some of these topics. And it was getting the job down here to come and occasionally they let me teach the cosmology course, which is one of the highlights of my year. Although if you're in my 141 class, physics 141, that's also the highlight of my year. So. But today I think that what we want to talk about is kind of delving into what does the Bible say about the origin of the universe. Of course, I can tell you a little bit more about what science says, but then it's like, well, what's the issue? How do Christians approach this topic? And so the first thing is, what does the Bible say? And the first verse of Genesis is actually really pretty. I mean, I just read this and I go, wow, right? In the beginning, God created the heavens and the earth. That's cosmology right there. Now, the earth was formless and empty. Darkness was over the face of the deep, and the Spirit of God was hovering over the waters. So the formless and empty, that's also cosmology. That's about what's there and how did it form, the structures of what exists. And down in verse 3 it says, and God said, let there be light, and there was light. God saw that the light was good. Oh, the origin of the light is also cosmology, by the way. And he separated the light from the darkness. God called the light day, and the darkness he called night. And there was evening, and there was morning the first day. And then he goes on into other things, which are like atmosphere of the earth, and who knows, whatever. And then some water under dry land, and stuff like this. And this is not so much cosmology. This is like, well, what's happening locally on Earth. And so us cosmologists, we don't care so much about that. But he gets back to it on the 4th day. He said, let there be lights in the vault of the sky to separate the day from the night, and let them serve as signs to mark the sacred times, days, and years, and let them the lights in the vault of the sky to give light on earth. And so it was. God made 2 great lights. What are the great lights? The sun and the moon. Yes. The greater to govern the day, and the lesser to govern the night. He also made the stars. Etc., etc. This is on the 4th day, and I think I wrote 3rd day someplace later, but that's okay. So a couple days later, we get back to some cosmology, and then it continues on with plants and animals and creatures, livestock, and eventually, man comes into the picture. However, there's a lot of other passages in the Bible that also talk a little bit about cosmology. The beginning of John starts out, in the beginning was the Word, and the Word was with God, and the Word was God. He was with God in the beginning. Through all things, through him all things were made. And so we get back to him all things are made. And that again is the origin of the universe. And nothing was made that hasn't made. So John is pretty definite about God creating everything that has ever been. There's quite a few other verses that talk about God, his invisible qualities. His eternal power and divine nature have been clearly seen and understood from what has been made. Remember, he made it all. So he's showing you himself through this universe that he created. You've made the heavens and the earth by your great power and outstretched arm. From him and through him and for him, all things are made. We have a reason to be here for him. My help comes from the Lord, maker of heaven and earth. If you can make that, clearly you can help me. That's nice, isn't it? The Lord is the everlasting God, the creator of the ends of the earth. By the word of the Lord, the heavens were made, their starry hosts by the breath of his mouth. And finally, our help is in the name of the Lord, the maker of heaven and earth. So there's all through Scripture, not just in Genesis and not just in John, but all the way through in the intervening time, there's this idea that God created it all. You can't get away from that in Scripture. So, what does it actually say about the origin of the universe? Well, it says there was a beginning. It does say there's a time when it started. Like, it didn't exist before the time it started. I don't know, is that too, like, philosophical to actually even say? But the Lord made the heavens and the earth. He spoke them into being. And then there's not a lot of historical detail about the events. He says, let there be lights. Let there be lights in the sky. So he's got this idea of night and day. And this should be paid for. Stars, sun, and moon on day. We learn just as much, through this telling of this, he made everything. We learn just as much about the nature of God as we learn about cosmology. Or actually, perhaps even more. You can tell me what you think. But it says that the Lord is present in his creation. Like he made it, and then he sticks around. So that's a new nature of God thing. Hovering over the water, my help is from the Lord. Never growing tired or weary. He seems to care for our well-being. He's a very personal God, even in the verses about cosmology and the origin of the universe. He is inconceivably powerful. I mean, if you could move a mountain, there's a place we sing in church, right? If you could move a mountain, right? But it's not just the mountain, it's the whole earth and the moon and then the sun and then our galaxy and all the other galaxies, right? And so at some point, the human brain cannot conceive of all the things he can move. And so that's why I say he's inconceivable isn't because we don't know what he's done, but the fact that we can't actually conceive the magnitude of that creative process. And therefore worthy to be glorified. And those are also in all the verses about God. So we learn a lot about God and not a lot of historical detail about the events. So cosmology is the scientific study of the structures that exist in the universe. Like when you say, what are we actually measuring? We're saying, well, there's stars here, and they orbit that, and it's that how things are built and structured in the universe from the top to the bottom. That includes the sun, moon, stars, planets, comets, etc., even the heavens and the earth. So all of those kinds of words are things that you see in Scripture, but we're also, well, not comets and planets, I don't think. But we're going to use those as well in cosmology to find out about their structure, where they're moving. So actually our view of the universe is very recent. And you might not really realize that people 100 years ago did not think of the universe the way we think of it today. But in 1925, Edwin Hubble used the secret variables to determine that this cloudy thing that they called the Andromeda Nebula was actually a galaxy of its own, not included as part of our galaxy. In 1950s, the galaxies were discovered that were gravitationally bound, and we either call them a group of galaxies, like our local group of galaxies, but we also talk about clusters of galaxies. Like galaxy clusters is a type of object that you can go look at. That was more in the 1950s. The large-scale structure was they started looking out there, realizing that there were sort of more clusters of galaxies in one part of the sky than another. And in 1998, they mapped some of the large-scale structures in the universe. And so I'm going to show you what those look like because they're kind of interesting. But the takeaway is really that modern cosmology is less than 100 years old. And all that really cool stuff like dark matter and dark energy are less than 20 years old. So if this was really important to God for our spiritual well-being, he would have written something about it in the Bible. But we're either super privileged, like the pinnacle of biological evolution, moving towards some sort of better life form for all this knowledge we have, or the knowledge of these structures is not really the important thing when God's talking about them in the Bible. One or the other. If these structures were super important to God in our spiritual well-being, he would have talked about them. I believe he would have talked about them. However, I still think it's really neat that we get to see things that, are only 20 years old. Are any of you more than 20? Awesome. So, our view of the universe. I need to actually, let's hit the front light off here because these are really pretty pictures. There we go. This is the Andromeda Galaxy, discovered in 1925 to be not a part of our galaxy, but a neighbor galaxy. We use this galaxy a lot to understand our galaxy because it's hard for us to see. Well, no one's ever gotten outside of our galaxy to take a picture. So this galaxy is the prototype. It's got its nice spiral arms. It has dust lanes and material. It's got a supermassive black hole at the center. It even has a little satellite galaxy, just like ours. We have large and small Magellanic Clouds that are sitting out here kind of like that. You're going to smack into us someday. Someday Andromeda is going to actually smack into our galaxy and all sorts of things, you know, disruptive orbits are going to happen. However, the picture that this was, that the universe wasn't just a bunch of stars in the dome above us, evenly spread out everywhere. That whole picture started in 1925. So in the 50s, these galaxy clusters were observed. In this picture, these are all galaxies. The yellow things are all elliptical galaxies that are actually gravitationally bound. And they're probably just like moving, you know, through back and forth, swinging kind of like a pendulum through the center of the cluster. But this cluster has a few hundred galaxies in it. These are not stars. These are actually galaxies all together in one spot that are bound together. And the large-scale structure, this is the map that they made in 1998. What they did was they said, Earth is here, and they looked up at a stripe of the sky one way, and a stripe of the sky the other way. And they put a dot on for every galaxy that they saw, with its distance from us, and also the angle in the sky. This is literally tens of thousands of galaxies now grouped and plotted on the map. They get to be sort of inefficient, so it gets a little dimmer out here, not because the galaxies don't exist, but it was hard to see. Okay? But if you look in here, you start to see something else, which are these groupings here of galaxies. Those are our galaxy clusters. And so the galaxy clusters are pulling material into them, and new galaxies, right? There's galaxies along these filaments as well, and those galaxies are going to move into the clusters in time. So the clusters are picking up additional galaxies as they can. But there's another feature here that this thing looks a little bit like Swiss cheese. So the clusters themselves are actually being pulled apart as the universe expands. And the Swiss cheese effect is due to the clusters themselves getting moved apart, pulled apart. And some galaxies get left in between too as you're pulling these things apart. There's a few that just dribble out there and they get lost, right, in between. So on these scales, these clusters are actually expanding or moving apart. And so, the Big Bang. It actually originated before any of this data or view of our modern world. It was sort of happening at the same time. But in 1917, Einstein argued for an eternal steady-state universe. When he looked up at the stars, he said, we can't be thinking that this was created at some time. It's just always got to be there. It's got to be there and just sitting there without moving, because otherwise, if it was moving, it would be either collapsing or expanding, and that would be terrible. Lemaitre, he actually took Einstein's equations and said, instead of being steady state, that we could actually model them as the cosmic age exploding at the moment of creation. He probably said it in French because he's Belgian. And he was not as disturbed by the idea of a creator because he was actually a Belgian priest who taught physics at a university. Okay, so he wasn't bothered by it. But he gave a colloquium. This is pretty funny. He gave a colloquium, and Einstein was there. And Einstein said to him, well, your math is excellent, but your physics is abominable. So, if Einstein said that to me, I probably would quit my job. So, the discovery that the universe was expanding happened just 4 years after the discovery of the Andromeda Galaxy. And at that point, it led many to abandon the steady-state universe idea, including Einstein. By 1935, Einstein and most of the cosmologists were sort of saying, no, it's not steady-state, it really is expanding. However, there were some holdouts, and so there was this big debate on the radio in 1949, and Sir Fred Hoyle he was a steady-state guy, and he goes, well, why don't you just call it Big Bang, or something like that. Anyway, it was not he did not see the word Big Bang as a positive comment to his, debate partner. But the name caught on, and so we've used that term ever since about 1950. The afterglow of the Big Bang was discovered in 1964, and I don't know of anybody who held on to the steady-state universe after that. So historically, there was this idea of what our universe looked like. Observationally, there was also this idea, the view of the universe having all these galaxies, et cetera, in it. So they were going on, the debate with how the Big Bang was going on for pretty much all of the 1900s, 20th century. So there is observational evidence of the Big Bang, and I think this is actually really important because as people, we want to know what's real, and we can make up all the theories in the world, but when we go out and look at the data, then we go, oh yeah, that theory is confirmed by what we see in the world. And so that's how science works. And there's actually quite a few features. I put 6 of them on the slide here, but I'm only going to go over the first 3 today, which are a modern-day Olber's paradox, the universe is expanding, and the afterglow. So Olber's paradox is like this. So you sit there and you look up and you see some stars in the sky. And you say, well, if there's stars everywhere, equally, dotting the sky landscape, I would eventually, my eye would intersect with a star if I looked out. No matter where I look. So if I take a picture, I need more stars than are shown here. I want this graphic to go out further. But if I took a view over here, I should see a star over there, right? Eventually I should see a star. And you can calculate the brightness of the sky, and what we calculate is that we should see light in all directions at night. And what do you see when you go out? You see a dark sky. Paradoxically, the night sky is dark. That is just a total mystery. Because if there's stars out there everywhere, we should see them. Well, we actually nowadays play this game with galaxies instead of stars, because we do believe that the stars are sort of, the stars that you look up and see at night are actually in our galaxy, and so that doesn't get us very far. We have to look at galaxies. We look out as far as we can. The Hubble Deep Field Survey was taken specifically to identify all the stars in a tiny little section of the sky as far as possible. It took something like 1,000 hours of Hubble observation time to produce this picture. And you see galaxies. I could stare at this thing all day. You see galaxies like side view on, You see galaxies. Well, this is actually a real star, because you can see the diffraction pattern of the struts of the Hubble telescope. But what you mostly see, about 95% of this is black sky. And Hubble says, we see black sky. We do not see the galaxies that are further away than these galaxies. Well, why should we not see galaxies that are further away than these galaxies? Only one reason. The reason is that the light from those galaxies has not had time to reach us. That was the point of taking this image. It was the main science driver for this image. And based on this, they can exactly say that the galaxies that are located further in the universe that we don't see are, that we don't actually see them. We don't just continually see those galaxies. So the fact that the light from the most distant stars has not had time to reach Earth is because the universe had a beginning 13.8 billion years ago. That's the reason the night sky is dark. And I think that's pretty cool.
So over time, we'll see more and more stars then, or galaxies then?
Yes, it actually depends a little bit on how the universe is expanding. If it expands faster, then you'll see fewer. If it shrank, you'd see more. But you're talking like one day isn't going to be enough to see a whole lot further, right? But if you went out another billion years, you'd see a different set of stars or galaxies out there. You'd see a different kind of beginning. So the second thing we see about the universe is that it's expanding. So Edwin Hubble went out and he measured galaxies, and these are 1 million parsecs and 2 million parsecs, and then he measured the doppler shift of the light, the redshift of how the wavelengths are shifted because of the motion of those galaxies, and measured the velocity of those galaxies. And he came up and he said, wow, look at that, we've got this nice linear line. What do you do with a line? You find the slope of the line. And the slope of the line is 70 kilometers per second per megaparsec. Actually, the slope of that line is 500 kilometers per second per megaparsec. But, he made a mistake, so it's still a line. If the universe was not expanding, you would have as many things going away from you as you would have coming toward you. So this half of the plot down here is the coming toward you part. There are some local things, like our local group, some of the galaxies are coming toward us and some are going away from us. But if you get out far enough into that Swiss cheese kind of regime where things are further apart, everything is actually moving away from us. And so the picture we have kind of looks like this. So you have to be the galaxy, okay? This is a real thing, but if you be the galaxy, and you look out and you go, look how far that guy is, it's this far away. And then you wait for a little expansion and you go, oh look, that galaxy's further away. So the galaxies that, when you look out, the galaxies that, this galaxy, this is us, is only moving a little bit fast, but this galaxy is moving a lot fast. And so you actually get this speed effect from being the galaxy and just looking out at everybody else around you. Every single galaxy is moving away if you get out into the Swiss cheese part of the universe. But for us, we can take this and turn it around and say, if they're moving away today, that means they were closer together in the past and closer together in the past. And what happens when you get all that stuff together? Those structures are all going to be disrupted. It's going to get hot and turn into a particle soup. And so when you rip all the galaxies apart and put them back in the early universe, you end up knowing that these structures would have come out of, little places here that were more dense or less dense are going to collect those stars around them. The stars are going to start to spin up into orbits, gravitate. Gravity is going to make these structures as that gets, pulled apart. So it is expanding. It's not like a theory. That's actually, you go to the stars and you see it. Today we actually look at supernovas for this. The reason is because if you look at a supernova, it's called a standard type 1A supernovas are standard candles. So you basically have a white dwarf star and some other big red giant star. And as this binary system is orbiting, matter will occasionally, in some of these systems, the matter from the big red star will accrete onto this white dwarf. And when a white dwarf gets to exactly 1.4 solar masses, it blows up and goes supernova. And it has exactly 1.4 solar masses of energy there to go supernova with. So it's the standard candle. It's always just as bright. Every type 1A supernova is just as bright as every other type 1A supernova. And so if you look at they explode and it takes them about 30 days to brighten and then dim. And if you look at the brightness during that period and figure out just exactly how bright it was, from our point of view, you can tell actually how far away it is. Because the further away things are, the dimmer they are. And so if you look at the brightness of something that you think is actually a standard candle, you can measure this velocity-distance relationship that Hubble did. So So we do it better, basically, now. In fact, we do it out. This is a redshift of this. I know I haven't defined the term redshift. I'll tell you what this plot means, though. That out here at a redshift of 1, this is half the age of the universe. So these supernovae here blew up 7 billion years ago, and we're measuring their velocity, and these blew up much more recently. And so we've actually measured this expanding feature over half of the history of the universe. That's to get to here. When you go past here, it's also measured. So about 2/3, 3/4 of the universe's time every year, you have to look it up and figure out what the highest redshift supernovae are. But that expansion has been measured for most of the universe, definitely more than half. So what does it say? Well, it says that things were hotter and particle soup-like before. That's why we want to get there. It actually says that there was a beginning. It points to the beginning. The third thing that points to the beginning is people said, okay, well, this was mid-1950s, and nuclear physicists got together and said, okay, let's say there was a particle soup. Let's say that particle soup was sitting out there. Well, as the universe expands, you might see the afterglow of, say, that original exploding thing. And so the afterglow of the original particle soup has also been observed. And that's a pretty important one. So here's how the story goes. If you're a hot particle soup, you have a spectrum that has very high energy light in it, photons. And those high energy photons can actually pull hydrogen atoms apart. Like if the universe has a lot of protons and electrons, they want to get together and be hydrogen all nice and neutral. But if you have a bunch of X-rays there, they'll pull the electrons off and leave you just with the proton and an X-ray that's now somewhere else. And so if it was hot, they said this whole thing would be ionized. As the universe cools, you end up with fewer and fewer X-rays to be there to get those, to pull those hydrogens and electrons apart. So at some point, the hydrogens and the electrons got together as the universe cooled. And once they were neutral, they didn't absorb the light anymore, pulling them, in the ionization process. And the light was then, so when the heat radiation was not energetic enough to keep the hydrogen, pulled apart, that radiation instead was able to stream freely across the universe. And so this hot, photons from that, we should be able to go and look at them. We actually have to, the universe continues to expand, so we see them at a cooler temperature than back then. But that's what we've actually seen when we say we've looked at the cosmic microwave background. First guys who did it, oops, it's supposed to say Wilson. Hansen and Wilson, 1964. Wow. They made a radio telescope. They were going to look at satellites and try to get, communications like from the Russians, whole thing. Right, and this is their microwave telescope. And, well, it wasn't working very well. All they saw when they turned it on was, they just saw a bunch of noise. No signal. It was like a battle day on the electronics, anybody taking electronics? Okay. Well, sometimes all you get is a bunch of noise on the oscilloscope. So the first thing they tried to fix that was they climbed up into the telescope and took the bird poop out. There were nesting birds in there.
Oh my word.
It's like, well, your PhD is more recent than mine. You go do that. Yeah. So they cleaned it out. Still nothing. And they got together with some theorists at MIT through a series of emails and things saying, oh, well, I predicted that there would be some microwave or radio signals at this frequency. And they went out and they had actually seen this enormously bright cosmic microwave background. So if our eyes could see in the radio and the microwaves, we would see Olber's paradox. The night sky would be tremendously bright with this radiation from the Big Bang. So if you go out into space and take any square centimeter, about that much, 100 microwave